Imagine a star cluster so dense it's a cosmic pressure cooker of stars, where gravity should have forged dozens of black holes, yet for decades, astronomers found only ghosts of their existence. Until now. Deep within the ancient heart of NGC 6101, a cluster 13,000 light-years away, a team of scientists has uncovered the first of these elusive giants. Using 20 years of Hubble's archival data and JWST's piercing gaze, they peeled back layers of stellar chaos to reveal a black hole hiding in plain sight. Its gravity so subtle, it slipped through telescopes for centuries. This discovery doesn't just fill a gap in the universe's inventory, it rewires our understanding of how these cosmic titans form and evolve. For every missing black hole found, 1,000 more mysteries linger. And this? This is the moment science finally caught up to the cosmos' secret recipe. In the vast tapestry of the universe, black holes are both enigmatic and essential, shaping the evolution of galaxies and star clusters. For decades, astronomers have puzzled over a mysterious gap in their understanding, a missing population of black holes that seem to defy predictions. Now, a groundbreaking discovery has filled that gap. Using over 2 decades of Hubble Space Telescope data combined with new observations from the James Webb Space Telescope, a team of astronomers has identified the first of these so-called missing black holes in a famous star cluster. This find not only resolves a long-standing mystery but also sheds light on how these cosmic giants form and evolve. Let's explore what this means for our understanding of the universe. To grasp the significance of this discovery, we need to revisit a fundamental question in astrophysics: how do black holes form in dense stellar environments? Star clusters, like the ancient globular cluster NGC 6397, are crowded with stars, some of which collapse into black holes. But when astronomers looked closely, they found a problem. Theoretical models predicted a certain number of black holes should exist in these clusters, yet observations didn't match. This discrepancy led to the idea of missing black holes, objects that should be there but had eluded detection. The new discovery in NGC 6397 is the first clear evidence of one of these elusive entities. NGC 6397 is a dense, ancient star cluster located about 10,000 light-years from Earth. It's one of the oldest known clusters, with stars dating back over 12 billion years. Such clusters are ideal laboratories for studying stellar evolution because their stars are all roughly the same age and composition. However, they also present a challenge. The sheer density of stars makes it difficult to spot individual objects, especially black holes, which don't emit light. For years, astronomers suspected that some black holes in these clusters might be hiding in plain sight, their gravitational influence detectable only through subtle effects on nearby stars. The key to uncovering these missing black holes lies in their gravitational interactions. When a black hole exists in a star cluster, its immense gravity can subtly tug on nearby stars, causing them to move in ways that reveal the black hole's presence. But detecting this requires precise measurements over long periods. This is where the Hubble Space Telescope's decades of archival data became invaluable. By analyzing the motion of stars in NGC 6397 over 20 years, the team could spot anomalies that hinted at the presence of a hidden black hole. However, Hubble's optical instruments have limitations when it comes to detecting faint, cool objects. Enter the James Webb Space Telescope, with its advanced infrared capabilities. Webb's ability to peer through dust and detect cooler objects allowed the team to confirm the black hole's existence and measure its properties with unprecedented precision. The process of discovery was both methodical and painstaking. The team began by examining Hubble's long-term observations of NGC 6397, searching for stars that exhibited unusual motion. They focused on stars near the cluster's center, where the density of stars is highest and the likelihood of a black hole's gravitational influence is greatest. Over time, they noticed a pattern: certain stars were moving in ways that suggested an unseen massive object was pulling them. These stars, known as velocity outliers, are a common indicator of hidden black holes. However, confirming this required more than just observations. They needed to rule out other explanations, such as binary star systems or stellar remnants. This is where Webb's infrared observations came into play. By capturing data in the infrared spectrum, Webb could detect the faint glow of objects that Hubble couldn't see. The team used Webb to study the same region of NGC 6397, looking for signs of a black hole's gravitational effects. They found that the star's movements aligned with the expected behavior of a black hole with a mass several times that of the Sun. This mass estimate is critical because it places the black hole in a category that had been missing from previous models. While stellar mass black holes form from the collapse of massive stars, intermediate mass black holes, those with masses between hundreds and thousands of solar masses, are still a subject of debate. The discovery in NGC 6397 suggests that these intermediate mass black holes might form in dense environments like star clusters, where gravitational interactions can merge smaller black holes or stellar remnants into a larger, hidden giant. The implications of this discovery are profound. For years, astronomers have struggled to explain the absence of intermediate mass black holes in the universe. Some theories suggested they might form in the early universe, while others proposed they could be the seeds for supermassive black holes found at galaxy centers. The detection of this black hole in NGC 6397 provides a concrete example of how such objects might form in dense stellar environments. It also highlights the importance of long-term observations in astronomy. The 20-year Hubble dataset was crucial, as black holes' gravitational effects are subtle and require decades of tracking to detect. This underscores the value of archival data, which can unlock secrets hidden in plain sight. Moreover, this discovery challenges existing models of star cluster dynamics. In dense clusters like NGC 6397, stars are packed so closely that their interactions are frequent and intense. These interactions can lead to the formation of binary systems, mergers, and even the creation of black holes. The presence of a hidden black hole suggests that these clusters might be more dynamic than previously thought, with complex gravitational interactions shaping their evolution. It also raises questions about how many such black holes might exist in other clusters, and whether they could be the missing link in the chain of black hole formation. The search for missing black holes is far from over. While this discovery marks a significant milestone, it's just the beginning. Astronomers are now turning their attention to other star clusters, using the same techniques to look for more hidden black holes. The James Webb Space Telescope's infrared capabilities are particularly valuable here, as they can detect objects that are too cool or too faint for traditional optical telescopes. Future observations might reveal a population of intermediate mass black holes hidden in the hearts of star clusters, providing new insights into their formation and role in the universe. In the broader context of astrophysics, this discovery bridges a gap between theoretical predictions and observational evidence. It reminds us that the universe is full of surprises, and that even with advanced technology, there are still mysteries waiting to be uncovered. The story of the missing black hole in NGC 6397 is a testament to the power of persistence, collaboration, and the relentless pursuit of knowledge. As we continue to explore the cosmos, each new discovery brings us closer to understanding the invisible forces that shape our universe. And in the quiet depths of star clusters, hidden black holes may yet reveal their secrets, one gravitational tug at a time. For decades, astronomers have been searching for missing black holes in dense star clusters, where the gravitational tug of these mysterious objects should be strong enough to leave a detectable signature. Yet, despite their expected presence, many black holes remain hidden, their existence inferred only through indirect clues. Now, a groundbreaking discovery has finally shed light on one of these elusive mysteries. By combining over 2 decades of archival data from the Hubble Space Telescope with the latest observations from the James Webb Space Telescope, a team of scientists has identified the first of these so-called missing black holes in a famous star cluster. But how did they do it? Let's dive into the process that turned decades of data into a revolutionary finding. The journey began with the Hubble Space Telescope, which has been orbiting Earth since 1990. Over its 30-year history, Hubble has captured billions of images, including thousands of observations of star clusters like the one in question. These clusters are dense, chaotic environments where stars crowd together, and any hidden black holes would be difficult to spot directly. Instead, scientists look for subtle signs, such as the way stars move around a massive, unseen object. But even with Hubble's powerful cameras, these signals can be faint, easily lost in the noise of countless other stars. The key to this discovery lay in the sheer volume of data. For over 20 years, Hubble's Advanced Camera for Surveys, ACS, had been systematically mapping the star cluster, capturing images in visible light. These observations, though valuable, had limitations. Visible light can't pierce through the thick clouds of dust and gas that often surround star clusters, obscuring the view of any hidden black holes. Moreover, the gravitational influence of a black hole on nearby stars is subtle, requiring precise measurements over long periods to detect. Hubble's data, while extensive, wasn't enough on its own. Enter the James Webb Space Telescope, launched in 2021. With its advanced infrared capabilities, JWST can peer through dust and detect faint, distant objects that Hubble couldn't. Infrared light, which has longer wavelengths, is less affected by interstellar dust, making it ideal for studying obscured regions of space. The team used JWST's near-infrared camera, NIRCam, to capture new images of the star cluster, focusing on areas where previous observations had hinted at the presence of a hidden black hole. These images provided a fresh perspective, revealing details that Hubble's visible light data had missed. But the real breakthrough came from combining these two datasets. The astronomers didn't just look at the new JWST images in isolation, they overlaid them with the decades-old Hubble data, creating a comprehensive view of the star cluster. This approach allowed them to track the motion of stars over time, a critical step in identifying the gravitational influence of a black hole. By analyzing the subtle shifts in stellar positions across Hubble's 20-year archive, they could detect patterns that suggested the presence of a massive, unseen object. The process was meticulous. The team first identified regions within the star cluster where stars exhibited unusual motion. These areas were potential candidates for hosting a black hole. Using Hubble's data, they mapped the trajectories of these stars, searching for deviations from the expected behavior. If a black hole were present, its gravitational pull would cause nearby stars to orbit it at higher speeds than they would around a normal, stellar object. However, the challenge was that these effects are tiny, requiring extremely precise measurements to detect. This is where JWST's infrared observations proved invaluable. The new data provided a clearer picture of the cluster's structure, helping the team isolate the region where the black hole might be hiding. Infrared light also allowed them to see through the dust that had previously obscured the view, revealing a more accurate map of the star's positions. By cross-referencing the Hubble and JWST data, the scientists could refine their models of the cluster's dynamics, narrowing down the possible locations of the missing black hole. The next step was to confirm the black hole's existence. To do this, the team used a technique called stellar kinematics, which involves measuring the velocities of stars in a region. They analyzed the motion of stars around the suspected black hole, looking for a pattern that matched what would be expected if a massive object were pulling them in. The results were striking. The star's movements suggested the presence of a black hole with a mass several times that of the Sun. But how did they know it wasn't just a dense concentration of stars or another massive object? The answer lay in the data's consistency across both telescopes. The gravitational effects observed in Hubble's long-term data aligned perfectly with the new JWST observations, ruling out alternative explanations. The team also compared their findings with simulations of star clusters with and without black holes. The only scenario that matched the observed data was one where a black hole was present. This confirmation was a critical moment, as it validated the decades of Hubble data and the new insights from JWST. But the discovery wasn't just about finding a black hole, it was about solving a long-standing puzzle. For years, astronomers had struggled to account for the number of black holes in star clusters. Some theories suggested that these objects were hidden by dust, while others proposed they were simply too faint to detect. This discovery provided concrete evidence that black holes can exist in these environments, even if their presence isn't immediately obvious. It also demonstrated the power of combining old and new data to uncover secrets that individual telescopes couldn't reveal alone. The collaboration between Hubble and JWST exemplifies the importance of long-term data collection in astronomy. Hubble's 20-year archive wasn't just a collection of images, it was a treasure trove of information that, when combined with the latest technology, could unlock new discoveries. The James Webb Space Telescope, with its infrared capabilities, built on Hubble's legacy, offering a new way to explore the universe. Together, these instruments showed that the answers to cosmic mysteries often lie in the intersection of past and present observations. This discovery also has broader implications. If a black hole can be found in one star cluster, it suggests that others may exist in similar environments. Future studies could use the same method to search for more missing black holes, potentially rewriting our understanding of how these objects form and evolve. The process of combining data from different telescopes and time periods highlights the collaborative nature of modern astronomy, where each observation builds on the last, creating a more complete picture of the cosmos. In the end, the search for the missing black hole wasn't just about finding a single object, it was about proving that the universe's secrets can be uncovered through patience, technology, and the power of collaboration. The Hubble and JWST telescopes, working in tandem, turned decades of data into a breakthrough that will inspire future generations of scientists to look deeper, farther, and longer into the cosmos. Combining over 20 years of archival data from Hubble with new data from the James Webb Space Telescope, a team of astronomers has found the first of the missing black holes. This part of our deep dive into Hubble Discovers the First missing black hole in this famous star cluster focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Combining over 20 years of archival data from Hubble with new data from the James Webb Space Telescope, a team of astronomers has found the first of the missing black holes. This part of our deep dive into Hubble Discovers the First missing black hole in this famous star cluster focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have puzzled over a peculiar gap in the cosmic census of black holes. These enigmatic objects, the remnants of massive stars, are expected to populate the universe in vast numbers. Yet, when we look at star clusters, dense, ancient collections of stars, something strange emerges. The number of black holes inferred from their gravitational effects doesn't match the number we can actually detect. Some black holes seem to be missing, hidden in the shadows of their stellar neighbors. Now, a groundbreaking discovery has changed that narrative. By combining over 2 decades of Hubble data with the latest observations from the James Webb Space Telescope, a team of astronomers has found the first of these so-called missing black holes in a famous star cluster. But this discovery is more than just a triumph of observational science, it's a window into a deeper mystery: why these black holes have eluded detection for so long, and what their absence might reveal about the hidden architecture of the universe. The star cluster in question, known as NGC 6397, is one of the oldest and most densely packed clusters in our galaxy. It's a cosmic laboratory, a place where the laws of physics are tested under extreme conditions. But even here, the presence of black holes has been a puzzle. Earlier studies suggested that NGC 6397 should contain a significant number of black holes, yet observations couldn't confirm their existence. This discrepancy led to a growing question: where are these missing black holes hiding? Some theories proposed that they might be lurking in the cluster's core, where the gravitational pull is strongest and the light from other stars could obscure them. Others speculated that these black holes might have been ejected from the cluster entirely, their escape propelled by violent interactions with other massive objects. But without direct evidence, these ideas remain speculative. The recent discovery of a black hole in NGC 6397 challenges these assumptions. Using a combination of Hubble's long-term monitoring and Webb's infrared capabilities, the team identified a black hole that had been invisible to previous observations. This black hole, estimated to be around 10 times the mass of the Sun, is located in the cluster's core, where the density of stars is highest. Its presence was inferred through subtle gravitational effects on nearby stars, a method that has been used to detect black holes in other environments. But what makes this discovery so significant is that it suggests there may be many more such black holes waiting to be found. If NGC 6397 is home to one of these elusive objects, how many others might be hiding in similar clusters across the galaxy? And if these black holes are so common, why have they remained undetected for so long? The answer may lie in the limitations of traditional observational techniques. For years, astronomers have relied on detecting black holes through their interactions with other objects, such as the X-ray emissions from accreting material or the gravitational wobble of nearby stars. However, these methods are not foolproof. Black holes that are isolated, not actively accreting matter, or located in regions of extreme stellar density can evade detection. In NGC 6397, the dense stellar environment likely plays a critical role. The cluster's core is a chaotic arena, where stars orbit each other in a gravitational dance. In such a crowded space, a black hole's gravitational influence might be masked by the sheer number of stars around it. Additionally, the intense radiation and stellar winds from nearby stars could make it difficult to observe a black hole directly, even with the most advanced telescopes. This discovery raises a new set of questions about the nature of black holes in dense environments. Are these objects more common in such clusters than previously thought? Or are they simply harder to detect due to their unique circumstances? The presence of a black hole in NGC 6397 suggests that the cluster's core might be a breeding ground for these objects, but it also highlights the complexity of their behavior. For example, the black hole's location in the cluster's core implies that it may have formed through a different process than isolated black holes. Some theories suggest that black holes in dense clusters could form through the collapse of binary star systems, where two stars evolve together and eventually collapse into a single black hole. Others propose that these black holes might have been formed in a different part of the galaxy and later migrated to the cluster through gravitational interactions. These possibilities challenge our understanding of black hole formation and evolution, suggesting that their life cycles are more diverse and dynamic than previously believed. But the discovery of this single black hole is just the beginning. Scientists are now grappling with the implications of this finding for the broader population of black holes in the universe. If NGC 6397 is home to one of these missing black holes, how many others might exist in similar clusters? And what does this mean for our understanding of the overall distribution of black holes in the galaxy? These questions are particularly relevant because the missing black holes could be a key piece of the puzzle in understanding how black holes grow and evolve. For example, if these black holes are more common in dense clusters, they might play a role in shaping the dynamics of these environments. Their gravitational influence could affect the motion of stars, influence the formation of new stars, or even contribute to the overall structure of the cluster. However, without more data, these ideas remain speculative. The discovery of this single black hole has opened the door to new possibilities, but it has also revealed the vastness of the unknown. Another mystery that remains is the role of the James Webb Space Telescope in uncovering this black hole. Webb's infrared capabilities allowed astronomers to peer through the dense stellar environment of NGC 6397, where visible light is scattered and absorbed by surrounding stars. This suggests that future observations with Webb and other next-generation telescopes could reveal more hidden black holes in similar clusters. However, there are still limitations to what these telescopes can achieve. For instance, the extreme density of stars in some clusters might make it impossible to distinguish individual objects, even with the most advanced instruments. Additionally, the presence of dust and gas in certain regions of the galaxy could further obscure the view, making it difficult to detect black holes in those areas. These challenges highlight the complexity of the search for missing black holes and underscore the need for continued innovation in observational techniques. The discovery also raises questions about the broader implications for our understanding of dark matter and gravitational interactions. While black holes themselves are not dark matter, their gravitational effects could provide insights into the distribution of mass in the universe. For example, the presence of a large number of black holes in dense clusters might influence the way dark matter is distributed, affecting the overall structure of these environments. However, this line of inquiry is still in its infancy, and more research is needed to determine the extent of these interactions. The fact that a black hole in NGC 6397 was found through its gravitational effects suggests that such methods could be key to uncovering other hidden black holes. Yet, the challenge remains in isolating these signals from the overwhelming background of stellar activity in crowded clusters. Perhaps the most profound mystery is the question of why these black holes have remained hidden for so long. Is it because they are simply too rare? Or is it because our methods of detection have been inadequate? The discovery of this single black hole suggests that the former may not be the case. If these black holes are more common than previously thought, their absence from our observations could indicate a fundamental flaw in our understanding of their behavior. For example, some theories propose that these black holes might be in a state of dormancy, not actively accreting matter and thus emitting no detectable radiation. Others suggest that they might be in a different phase of their life cycle, such as being part of a binary system that hasn't yet revealed their presence. These possibilities challenge the assumptions that have guided our search for black holes and force us to reconsider the ways in which we define and detect these objects. The search for missing black holes is not just a technical challenge, it's a philosophical one. It forces us to confront the limits of our knowledge and the assumptions that underpin our understanding of the universe. For centuries, astronomers have relied on observation to build models of the cosmos, but the discovery of this black hole reminds us that even the most advanced instruments have blind spots. It also highlights the importance of long-term observational campaigns, like Hubble's 20-year archive, which provide the kind of data needed to detect subtle changes over time. Without such persistence, many of these hidden black holes might never have been found. This discovery is a testament to the power of patience and collaboration in scientific inquiry, but it also serves as a reminder that the universe is still full of surprises. As we look to the future, the discovery of this missing black hole opens up new avenues for research. Scientists are now working to refine their models of black hole formation and distribution, incorporating the new data from NGC 6397. They are also exploring the possibility of using gravitational wave detectors to identify black holes in dense clusters, as these instruments can detect the ripples in spacetime caused by merging black holes. Additionally, the upcoming missions of the James Webb Space Telescope and other next-generation observatories will play a crucial role in uncovering more of these elusive objects. However, the search is far from over. Each new discovery brings with it a host of new questions, and the mystery of the missing black holes is likely to remain one of the most intriguing puzzles in modern astrophysics. In the end, the discovery of this black hole in NGC 6397 is more than just a scientific milestone. It's a reminder of how much we still have to learn about the universe. The fact that such a massive object could remain hidden for so long challenges our assumptions about detection, formation, and the distribution of matter in the cosmos. It also underscores the importance of continued exploration and the need for innovative methods to peer into the unknown. As we move forward, the search for missing black holes will undoubtedly lead to new insights, but it will also reveal the vastness of the mysteries that still lie beyond our current understanding. The universe, after all, is a place of endless wonder, and the story of these missing black holes is just one chapter in a much larger, unfolding narrative. As we stand on the brink of a new era in astrophysics, the discovery of this hidden black hole in the heart of a star cluster is more than just a triumph of observational technology, it's a beacon guiding us toward deeper mysteries. The Hubble and James Webb Space Telescope have already rewritten the story of black hole demographics, but their work is just the beginning. What comes next? A constellation of upcoming missions, instruments, and observations promises to expand our understanding, confirm existing theories, and even challenge the foundations of what we think we know about these cosmic giants. Let's explore how the next decade of exploration will shape our grasp of black holes and the universe they inhabit. The first step in this journey lies in the Nancy Grace Roman Space Telescope, a successor to Hubble and JWST that is set to launch in the mid-2020s. This telescope, named after the NASA scientist who championed the concept, is designed to conduct wide-field surveys of the cosmos, capturing vast swaths of the sky in unprecedented detail. Its primary mission includes mapping dark matter and dark energy, but its capabilities extend far beyond. By combining its high-resolution imaging with advanced data analysis techniques, the Roman telescope could uncover more of these elusive black holes, particularly those hidden in dense star clusters or obscured by interstellar dust. Its ability to detect subtle gravitational lensing effects, where the gravity of a massive object warps light from distant sources, may reveal black holes that have eluded previous surveys. In doing so, it could help us answer a critical question: are these missing black holes the exception, or are they the rule in the universe's hidden architecture? Complementing the Roman telescope's efforts will be the European Space Agency's Euclid mission, set to launch in the early 2020s. While Euclid's primary focus is on unraveling the nature of dark energy, its instruments are also optimized for detecting faint, distant objects. By mapping the distribution of galaxies and their gravitational influences, Euclid could indirectly trace the presence of black holes through their gravitational effects on surrounding matter. This approach, known as weak gravitational lensing, has already hinted at the existence of massive, unseen objects in distant clusters. If Euclid's data aligns with the Hubble and JWST findings, it could provide a broader context for the missing black holes, suggesting that their absence from earlier surveys is not a flaw in our methods but a reflection of their hidden nature. However, if discrepancies arise, it might prompt a re-evaluation of our models for black hole formation and evolution, forcing astronomers to consider alternative explanations for their scarcity. Beyond space-based observatories, the next frontier lies in the realm of gravitational waves. The Laser Interferometer Space Antenna, LISA, a joint project between NASA and ESA, is set to launch in the 2030s. Unlike traditional telescopes, LISA will detect ripples in spacetime caused by the mergers of massive objects, including black holes. These gravitational waves offer a unique window into the universe, allowing scientists to observe events that are invisible to optical or radio telescopes. For instance, when two black holes collide, the resulting gravitational waves can be detected long before the merger itself, providing insights into the population of black holes in the cosmos. If LISA confirms the existence of a large number of missing black holes, it could revolutionize our understanding of their distribution and behavior. However, if the data reveals an even greater discrepancy between predicted and observed black hole numbers, it might indicate that our current theories about stellar evolution or black hole formation are incomplete. Such findings could spark a new wave of research, challenging scientists to rethink the life cycles of massive stars and the processes that govern their final stages. On the ground, the next generation of telescopes is poised to revolutionize our ability to study black holes. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built, with a mirror spanning 39 meters. Once operational in the late 2020s, the ELT will provide unprecedented resolution and light-gathering power, enabling astronomers to peer into the hearts of distant star clusters and galaxies. Its advanced adaptive optics systems will correct for atmospheric distortions, allowing for sharper images of faint objects. This capability could be crucial in identifying black holes that are too dim or too obscured to detect with current instruments. Additionally, the ELT's spectroscopic capabilities will allow scientists to measure the velocities of stars near potential black hole candidates, providing indirect evidence of their presence. By analyzing these velocity shifts, astronomers can infer the mass and location of black holes, even if they remain invisible to direct observation. Another groundbreaking project on the horizon is the Square Kilometre Array, SKA, a next-generation radio telescope network spanning multiple continents. Scheduled to begin operations in the 2030s, the SKA will consist of thousands of antennas working in unison to create the largest and most sensitive radio telescope ever built. Its ability to detect faint radio signals from distant objects makes it uniquely suited for studying black holes and their environments. For example, the SKA could detect the radio emissions from accretion disks, hot, glowing regions of gas and dust that swirl around black holes, as well as the relativistic jets that sometimes erupt from their poles. These emissions provide critical clues about the mass, spin, and activity of black holes, even when they are not actively consuming matter. By combining SKA data with observations from other telescopes, astronomers could build a more comprehensive picture of black hole populations, including those that have eluded previous surveys. The synergy between these missions and instruments will be key to advancing our understanding. For instance, the Roman telescope's wide-field surveys could identify potential black hole candidates, which could then be studied in greater detail by the ELT or SKA. Similarly, gravitational wave detections from LISA could pinpoint the locations of black hole mergers, guiding follow-up observations with other telescopes. This multi-messenger approach, combining data from different types of observations, will allow scientists to cross-check findings and build a more accurate model of black hole demographics. However, this collaboration also introduces new challenges. The vast amounts of data generated by these missions will require sophisticated algorithms and machine learning techniques to process and interpret. Astronomers will need to develop new methods for analyzing complex datasets, ensuring that no potential black hole is overlooked in the vast expanse of the universe. Beyond confirming the existence of missing black holes, these future missions could also challenge existing theories. For example, if the Roman telescope or Euclid reveals that black holes are more prevalent in certain regions of the universe than previously thought, it might suggest that our models of galaxy formation are missing key components. Alternatively, if LISA detects a population of black holes with masses that don't align with current predictions, it could indicate that our understanding of stellar evolution is incomplete. Such findings would not be a setback but an opportunity to refine our theories, pushing the boundaries of what we know about the cosmos. The scientific process is inherently iterative, and each new observation has the potential to reshape our understanding, even if it means revisiting long-held assumptions. Moreover, the search for missing black holes is not just about numbers, it's about understanding their role in the universe. Black holes are not isolated entities, they influence their surroundings in profound ways. For instance, supermassive black holes at the centers of galaxies are thought to regulate star formation by heating and dispersing gas. Smaller black holes, like the one recently discovered, may play a role in shaping the dynamics of star clusters. By studying these objects in greater detail, future missions could shed light on how black holes interact with their environments, potentially revealing new insights into the life cycles of stars and the evolution of galaxies. This interconnectedness underscores the importance of continued exploration, as each discovery builds on the last, creating a mosaic of knowledge that stretches across the universe. As we look to the future, it's clear that the quest to find missing black holes is far from over. The Hubble and James Webb Space Telescope have already demonstrated that even the most elusive objects can be uncovered with the right tools and techniques. But their work is just the beginning. The Nancy Grace Roman Space Telescope, Euclid, LISA, the Extremely Large Telescope, and the Square Kilometre Array represent the next chapter in this story, a chapter that promises to expand our understanding of the universe in ways we can only begin to imagine. These missions will not only confirm the existence of more missing black holes but also challenge our assumptions, refine our theories, and open new avenues of research. In doing so, they will ensure that the discovery of this first missing black hole is not an endpoint but a milestone in a much larger journey, one that continues to unfold as we peer deeper into the cosmos. Ultimately, the search for missing black holes is a testament to the power of human curiosity and the relentless pursuit of knowledge. Each new observation, each breakthrough, and each unanswered question drives us to look further, to ask more, and to explore the unknown. The universe is vast, and its secrets are waiting to be uncovered. With the next generation of instruments and missions, we are not just observing the cosmos, we are becoming part of its story, writing new chapters in the ever-evolving narrative of discovery. For years, astronomers have puzzled over a cosmic mystery: where were the missing black holes? Recent observations suggested there were far more black holes in the universe than our telescopes could detect. Now, a groundbreaking discovery has finally shed light on this enigma. By combining over 2 decades of Hubble data with the latest insights from the James Webb Space Telescope, scientists have identified the first of these elusive black holes hidden within a famous star cluster. This finding doesn't just fill a gap in our understanding, it reshapes how we think about black holes and their role in the cosmos. Let me explain. For decades, astronomers studied star clusters like the globular cluster Messier 13, a dense collection of ancient stars. These clusters are ideal laboratories for studying stellar evolution, but they also posed a puzzle. Earlier surveys suggested there were more black holes than could be accounted for. Some theories proposed that these black holes were hiding in plain sight, perhaps buried within the cluster's dense stellar environment. But without direct evidence, the mystery lingered. Enter the Hubble Space Telescope. For 20 years, Hubble captured detailed images of Messier 13, revealing thousands of stars. Yet, something was missing. The team noticed an unusual pattern: certain regions of the cluster lacked the expected number of stars. This discrepancy hinted at the presence of massive, invisible objects, black holes. But how could they confirm this? Enter James Webb. With its advanced infrared capabilities, Webb pierced through the cluster's dense stellar haze, revealing hidden details. By analyzing the motion of stars around these regions, the team detected the gravitational signature of a black hole. This was no ordinary black hole, it was a medium-sized one, with a mass around 10 times that of the Sun. Such black holes are thought to form from the collapse of massive stars, yet they're notoriously difficult to detect. Unlike the bright, accreting black holes we often see, this one was quiet, blending into the cluster's stellar chaos. The discovery is significant because it addresses a long-standing discrepancy in black hole populations. Previous surveys suggested there were more black holes than our telescopes could account for. Some theories even proposed that these missing black holes might be wandering the galaxy, undetected. But this finding suggests they're hiding in crowded environments like star clusters, where their presence is masked by the sheer density of stars. This discovery also hints at a broader picture. If star clusters are hiding black holes, they could be a major reservoir for these objects. It challenges our assumptions about how black holes form, evolve, and interact with their surroundings. Moreover, it underscores the power of combining decades of archival data with cutting-edge technology. The Hubble telescope, launched in 1990, has been a cornerstone of astronomical discovery. Yet, even with its remarkable capabilities, it couldn't see everything. Webb's ability to peer through cosmic dust and detect subtle gravitational effects has unlocked new possibilities. This collaboration between old and new instruments exemplifies how science progresses, not by discarding the past, but by building on it. So what does this mean for the future of black hole research? It suggests that many more of these elusive objects may still be hiding in star clusters and other dense regions. It also highlights the importance of long-term observational campaigns. The 20-year Hubble dataset was crucial to this discovery, showing how patience and persistence pay off in astronomy. As we continue to explore the universe, we'll likely find more surprises. Black holes, once thought to be rare, are now understood to be more numerous and diverse than we imagined. This discovery is a reminder that the cosmos is full of hidden stories waiting to be uncovered. If you enjoyed this deep dive, consider subscribing to FactVerse for daily explorations of the universe's greatest mysteries. And if you have your own theories or questions about black holes, drop them in the comments, we'd love to hear your thoughts. Until next time, keep looking up.